I'm Natasha, and I'm going to talk about build infrastructure and build engineering. I like to give talks about this because, mostly to evangelize. This is an area that I think, in general, software developers, development teams, sometimes even very, otherwise very large, very mature development teams don't emphasize enough. And sometimes we take for granted the pieces we have in place, but don't necessarily analyze the pieces that we haven't really taken the time to expand upon and really put a good system in place. So, yeah, I hope you find it informative. So, I guess just to get started at a high level, you might ask, what is build engineering, right? It's actually a pretty hard question to answer, I think, but the way I generally look at it is that to me, it's the glue that holds the rest of the software development process together. And in practice, this can mean a few different things. So one example could be like choosing, configuring, or customizing, or maintaining a continuous integration server. It could be applying or optimizing development models, like branch-based development models versus patch-based development models, or something like that. It could be working on low-level build optimizations, so implementing distributed builds or bulk builds, something like this, or a lot of other things. But there's a few of these that I think are very, very fundamental and particularly important and useful for new development teams and especially in startups. So those are the ones that I'm going to talk about in particular today. But you might ask, why do I care? Well, as for why you should care, that's an awesome question, and I hope you walk away with an answer. I can tell you a little bit about why I care. So, yeah, as I said, my name is Natasha. And I live in Copenhagen, Denmark. I'm American, though. That's why I have an American accent. I moved there about 6 years ago to work for a company called Unity. I'm the lead of engineering tools at Unity. And at Unity, we make the Unity game engine. It's actually one of the most prominent game engines in the world. So when I started working at Unity in 2010, the company was a company of about 80 people or so. And it was very much still in startup mode. It was kind of at that sort of mature startup phase where companies are trying to figure out how to not be a startup but haven't figured that out yet. And I started there as the first dedicated build engineer. Now in 2015, the company has grown to somewhere around, I think it's around 800 people. And I lead a team of 10 full-time developers and some students that together make up the engineering tools team at Unity. So there are a few different development teams at Unity that are focused on consumer-facing products and services, but my focus is on engineering tools for the core product, so the actual engine itself. I'm also very passionate about open source software, and I'm a big advocate for the use of open source technology within proprietary software companies. Both the adoption of open source and the participation of companies in open source communities themselves. And you can see this actually as a trend in Unity itself. We're very active in trying to contribute to and improve the tools that we use. So for your reference, after this talk, the slides are going to be available on my own website, where I have my speaking history. Then there's also links to slides and videos for various other talks that I've given about lots of different things. And if you'd like to get in touch with me after the conference, you can do so on Twitter or by email. So I've also put that on the slide here for you. Twitter is by far the best way, at least for casual stuff. So now I mentioned that I worked at Unity Technologies, where we make the Unity game engine. For those who don't know, yeah, like I said, Unity is a game engine and a content creation toolkit. So yeah, so Unity is the engine that's powering some games that you may or may not heard of. Depends on what you're interested in. Some examples are Hearthstone, is a Unity game. City Skylines, Endless Legend, Angry Birds 2, Kerbal Space Program. These are all Unity games. And so, yeah, that's all well and good, and I'm super enthusiastic about Unity and about games, but let's get a little bit more technical. So what is Unity? So Unity is an editor that game developers use to make their games. The official editor runs on Mac OS X and on Windows. The editor for Linux is currently in experimental build and testing. It has a runtime that is, which is the engine itself, that's currently ported to 22 different platforms. Unity itself is mostly written in C++. The gameplay scripts that users will use to write their game logic is written in C#. And this means that we have a platform-independent scripting language, or a scripting engine built into Unity that's built on top of Mono. Our main code base is a few million lines of code, and it has over a few hundred different build and test targets that can be run. To get full editor installers of our product, we have build chains that go several layers deep, and they take hours to build. Many of our platforms are console or mobile platforms, which are very heavily constrained in terms of tools. We're very heavily constrained in terms of tools by what basically the vendors decide to make available and how they choose to make things work. And game engines also generally contain a lot of third-party middleware that has to be integrated, and Unity is definitely no exception. So as you can imagine, this all proves to be very difficult and complicated from a build engineering standpoint. So I'll just go over a little bit of history of build engineering at Unity. So in 2010 when I started, as I mentioned, we were still very much in startup mode. And this is what I had to work with. So we had a very unstable Subversion server. It suffered regularly from corruption. The coffee machine also didn't work, so there was a label on the coffee machine saying powered by Subversion. We had a workflow where all of our developers just committed directly to trunk, which meant that various targets were often broken on one platform or another. Our code base was set up in such a way that we had we had an unstable continuous integration server on top of the unstable Subversion server. And our code base was being built with these static, like Visual Studio and Xcode projects that were all wrapped up in Perl. Perl was the legacy choice. We still have Perl in our code base for legacy reasons, but it was like we didn't really have a low-level build system. We just had a bunch of project files that there was some Perl script sort of gluing together. So that meant that whenever somebody wanted to add a new file to the code base, he had to go find all 6 of these project files, add the file to each one, even though many of those actually wouldn't compile on the platform that he was on. And we didn't use a distributed version control system, so there wasn't a good way to pull from one machine to another to test either. We had a few automated tests on a couple of platforms, and all of this building and testing happened on a small cluster of just 4 machines. And this meant that on a good day, if we were lucky, we might get a full build of our code base through the build server. And then finally, from a deployment perspective, we also weren't doing so well. Our deployment scripts were running directly off of developer machines, and they had absolutely no built-in verification for the integrity of deployed builds. So yeah, that's an interesting trip down memory lane for me, but if you look at where we're at now, in 2015, we have distributed version control with Mercurial, where developers are using branch-based development. Instead of static project files, we have a real build system that generates our platform and IDE-specific project files. We have a stable continuous integration solution in place now. This is an internally developed open source solution that was about a 1.5-year long project for the build automation team. We have now automated tests running regularly on developer branches and on our main line. On a cloud of over 200 different machines, many of which are connected to various mobile devices or game consoles. And we developed a web-based publishing portal that we use for publishing builds. And so that sounds great, but you might ask, what did it accomplish? Well, The biggest change is that our release cycles actually went from as long as 18 months between feature releases to every 3 months. We now ship on a strict time-based release cycle. Our alpha and beta builds went from somewhere between every like 2 to 6 weeks to every week, like clockwork. And all of this actually happened while our development team grew over 400%. So this is particularly impressive because, as many of you know, especially if you're used or familiar with this concept of like the mythical man month, often, more times than not, usually throwing more programmers at a problem will slow development down rather than make it faster. So looking at Unity is a bit of a case study. We talk about like the foundation of build infrastructure that I think has helped make all of this possible. I sometimes use the terms build engineering and build infrastructure interchangeably, but I generally think of build infrastructure as the tools, services, and procedures that you use to implement build engineering practices. So let's proceed. In terms of foundation, I think there's sort of what I call the 5 pillars of build infrastructure, and I've listed them here. These are one-click builds, build automation, continuous integration, automated testing, and automated deployment. I consider these to be the 5 pillars of build infrastructure just because I believe that they're fundamental to holding up a productive and efficient development process. And one thing to note here is that these points sort of assume that you're already using version control already. I could do an entire talk on why you should use version control, the different ways that you can use it, the different development practices you can build on top of your version control system. But that's unfortunately outside the scope of this presentation, even though it's a topic that I really, really love to talk about. So I'll cover each of these points briefly and tell you a little bit about what we managed to do at Unity over the years. But there's a really good chance, you know, considering the fact that we're a PyCon, you might be asking, like, what on earth does all of this have to do with Python? The answer to that's also quite simple. Python is just an amazing language for writing development tools. Whether it's the extensive web stack, the platform portability, the fast iteration time that developers get from using Python, it really, really is a great choice. So at Unity, we use Mercurial for version control, which is written in Python. 3 of these 5 pillars that I've talked about and we'll talk more about are also implemented using Python. And I believe in particular as well, this kind of shows how Python can still have a place in an environment where native performance means everything. So whenever it comes to game tech, like there's obviously a huge, huge emphasis on being able to get very, very high-end performance. And this becomes a bigger and bigger issue, especially as like there's more and more emphasis on mobile technologies. Now we have VR and we have AR. So there's this huge emphasis on performance, but this shows that like even in this industry, in this environment where there's a huge emphasis on performance, Python can still play a really, really vital and appropriate role. So let's just go through a few of these points. So the first one of these is one-click builds. And this obviously means simply being able to build software with one click rather than having to paste in some super complex command to a terminal or following some other complicated build process. So this is something that like people often kind of take for granted as like, well, you know, it's not even worth talking about. That's just something that you have. But I think that this is something that often we don't think about quite enough. It gets easy to get into a situation where it's almost a one-click build. If you happen to have this tribal knowledge that you need to configure this one thing on your machine this certain way, or you have to have this one particular setting in your terminal or something like that, and we sort of lose sight of this like out-of-the-box one-click mentality. Obviously, why you want these for a few reasons. Like one is the sort of the KISS principle, right? One-click builds are just simple and they increase developer productivity. They encourage developers to build early. They encourage developers to build often. But perhaps most importantly, they're a sort of a piece of fundamental groundwork for software development principles. In terms of getting started, like obviously what you want to do depends a lot on your particular application. You can implement a solution with a Python-based solution like Scons or WAF. When I give talks about like building specifically, one of the things I talk about is how I think build systems should be very cohesive, and there should be one point of entry. This is actually a principle that we violate at Unity, and that's why we're replacing our build system. But it's all of those sorts of things. Like it's not just about having this one-click build system, but it's about making sure that you implement that well, and then you maintain that so that the developer experience doesn't degrade over time. Another thing to think about is platform dependency issues. One example of this, of a platform dependency issue that could be mitigated with a properly designed build system I mentioned earlier, was that our old build system had a serious issue where developers were expected to find several different solution and project files and add source files to them, even though they couldn't test these or know if they missed one because they didn't all run on their platform. With a better build system that instead generates these project files, like that issue is gone. Just briefly, what does Unity do about this? So our current build system this is actually one of the things we don't use Python for. Our current build system is built with Jam+ and Perl. Jam+ is the low-level language, and Perl is used for kind of high-level scaffolding. Perl is primarily there because of legacy reasons. Jam+ was chosen years ago for its speed with complex dependency chains. Unfortunately, like, we didn't really find a good Python-based tool for this that met all of the requirements we had. We started looking last year to migrate our build system to something more modern. And we ended up choosing Gradle, which is a very, very odd choice, no doubt. I gave a talk about how we made that decision at the Gradle Summit this year. It's about a 45-minute talk, and I totally recommend watching the video if you are particularly interested in how we ended up there. Yeah, so next, build automation. This is basically setting up a build server that will run the one-click builds that I just talked about. So obviously the main benefit of build automation is just verification, right? Some software developers are really familiar with the phrase of like works on my machine. Like my husband is also a programmer, and I'm always giving him all kinds of crap because he's like king of this phrase. It never breaks on his machine, but it does on everyone else's. Building on a build server, it allows for verification of the build in an objective environment. It helps you figure out, for example, if that one-click build that you implemented isn't exactly a one-click build anymore. If you have a large code base with allotted build targets and a complex dependency chains like we do whenever we build Unity, it also gives you this benefit of parallelization, right? And then once again, it's just a groundwork for other things that you need to have an efficient development process. So getting started, obviously you want to pick and evaluate and pick a build server solution. The right one's going to depend on what you need. In my opinion, a good Python-based solution is BuildBot, but it's worth noting that BuildBot is really more of a framework rather than a top-to-bottom solution. In terms of advice, one of the things that I'm always really pushing for at Unity, and I always push people whenever I give talks about this, is to pay a lot of attention to where you do configuration in your low-level build system versus where you do configuration at the build server level. In my experience, developers often want to push as much configuration into the build server itself because it seems convenient in the short term. But this leads to very overly complex build server configurations, which can then become fragile and hard to maintain. And especially if you combine that with something like branch-based development, you can get into situations to where the build server configuration only works on new branches or something like that. So in terms of how Unity does this, we have a custom build automation solution built on top of BuildBot. We gave it the codename Katana, and it's written entirely in Python. Of course, it's open source. The source is available on GitHub. We're by far the most active users and the people who are actively developing it, but there are other organizations that use it, and I would totally encourage you to give it a look if you're looking for something to solve this particular problem for you. It's built on top of BuildBot, so it uses the same technologies as BuildBot, we've implemented like a new UI and a real-time solution based on top of Autobahn, for example. The lead backend developer on the Katana project wrote on her blog how to get started with Katana. It's a great place to go if you want to find out more information. But if you are already familiar with BuildBot, it will be quite familiar to you. And then it's worth noting that Katana's build cloud is configured with an awesome Python tool called Salt. Check it out if you're looking for a tool to help you automatically configure machines or install software. We've done some work on Salt, contributed some patches to Salt to get it working better on Windows in particular. But I would definitely recommend giving that a look, and you can find out more about it at saltstack.com. So the next thing is continuous integration, which is just continuously running these automated builds. Why would you want this? Well, obviously it increases developer productivity in a lot of different ways. Perhaps the most prominent way that it increases productivity is by avoiding integration hell. And this is usually just a term that we use for referring to the situation where you have multiple lines of development and they just collide with one another without any history of what actually broke what. In that case, you have to do a lot of manual bisecting to try to sort out what happened. But if you're doing continuous integration, you'll have a system that will automatically identify your exact failure point as early as possible. In terms of a solution, generally you'll be using the same solution as for build automation. The solutions that I previously mentioned can be configured to do continuous integration, run nightly builds to do whatever you need. And one thing to note is that sometimes like continuous integration doesn't make sense or isn't feasible, and in that case, what we call frequent integration is good enough. So at Unity, we don't actually do true continuous integration yet. But we actually are working on scaling our infrastructure to allow for this because the development team's gotten big enough now that it's really badly needed. We do frequent integration, which means we do nightly builds on all main lines, nightly builds and tests. We do on-demand builds on developer branches, basically whenever developers have reached milestones and they believe that they're ready to have their code built and tested. One big lesson learned here for us is that continuous integration itself can often be a really huge waste if your development model and history is useless. So if developers are pushing changes that they don't even expect are going to compile or going to compile on all machines, then it's quite wasteful to expend like build automation resources on actually doing true continuous integration. Yeah, so the next to last thing is automated testing. This is the automated execution of tests on your continuously running builds. So probably most of you are familiar with automated testing and some of the benefits of them, but I'll just cover it briefly. Yeah, so why would we want to do this? Well, an obvious answer is that it helps protect against regressions. It saves human resources, both by allowing you to, in some cases, not all, but in some cases, replace manual test points with programmatic testing. But it also removes the burden on developers to necessarily run all of the test suites locally. And if you have a lot of high-level or slow tests, that can be quite beneficial. And then finally, it keeps the test suites from bit rotting. If you put the effort into creating a nice test suite, it's a really nice way to ensure that it stays up to date, right? This is another case where the solution is going to depend on your product. If you're working on low-level tests, you can often pick a test framework that's built for your technology. And then sometimes it makes sense to create your own frameworks. This is particularly true if you have a need for a lot of very high-level automation, high-level integration tests. It's particularly, or like Unity is a very large piece of software, for example, with a lot of moving parts. And it's particularly prone to the case where you have to tweak one something to handle one platform, and that adjustment might cause a problem on another platform that you don't expect. Often it isn't possible to catch these sorts of things with low-level unit tests, so we have a lot of high-level integration tests. We have a whole team of developers who work just on developing and improving these custom frameworks. So at Unity, in terms of technologies, we don't use Python for this either. The test frameworks are not owned by the engineering tools team, but even if they were, I don't really think the picture would look any different. Our test frameworks are all written in C#, and this is actually a good language for us because it is a nice language that's familiar to all of our developers. It has good development tools. We make very heavy use of in-unit, and we have a custom test runner that's written in Perl. The choice of Perl is mostly because there's other Perl in the code base, and all of the developers are guaranteed to have a Perl interpreter, like even if they're on Windows, and most of them are. And then this last little bit, automated deployment. The most basic benefit of automated deployment, right, of builds that you want to publish is that it's less error prone than manual publishing. You're able to remove an element of human error here, which when you're talking about pushing data to production servers that your customers will access is really valuable, especially in today's climate of software as a service. It's extremely important. Automating your deployment will allow you to add programmatic verification, like checksum verification, for example, to your deployed binaries. And it also provides a convenient way to start tracking your history programmatically, your release history. So you have a hook to start logging what was published, when it was published, and who published it. The solution for this is often going to be related to your build automation. If you aren't doing your publishing directly from your build server, and you might not want to for good reasons, then it's probably going to pull builds from that build server, right? Most likely through some sort of API. The final solution will depend a lot on your organization's server infrastructure, the type of software, for example, whether or not you're using a content delivery network, and how many binaries you have and what size they are. Just start with a simple script and expand from there. Let's see. So at Unity, we have a web-based publishing portal called SciHi. In case you didn't know, all of our tools are modeled after Japanese weapons. This is written as a relatively simple Django application, for example, and it's used for promoting builds to internal QA and publishing to external testers. It publishes to the CDN, and it also provides an API that other internal services use for getting information about what builds have been released and providing the download links. So just to wrap up quickly, these 5 points, I talked about them in a list earlier, but I think that they're better described in this format, where each one sort of paves the way for the next one. And the last thing that I would say is that just do something. Like, try to make this better within your own teams. It's unlikely that you're working in an organization that doesn't have these things implemented in some way. It may be the case that you have all of them, but it's very unlikely that you've taken the time to really analyze each point and figure out if it's really as complete and robust as it could be. So go back to your own teams, try to make these things better. Sometimes people are change averse. These are the types of tools people often don't like to change. So try to focus on the positives. And finally, don't underestimate the value of having dedicated build engineers on your team. So yes, the guys at work would kill me if I didn't let you know that we're hiring. So these are the sorts of people we're looking for, in particular good Python programmers, especially for my team. Come check us out. And yeah, then if you would like to get in touch with me, please do so. And I'll be here for a bit longer today. So thank you.